Hi. In this video, we're going to be looking at the solutions to Newton's second law, worksheet 1. And we're going to start off right off easy. What's the equation that Newton's second law gives us? This comes from the acceleration is equal to the force divided by the mass. So acceleration is directly proportional to the force. As the force goes up, so does the acceleration. And it's inversely proportional to the mass. So as the mass goes up, the acceleration goes down. The first problem we're going to look at is this pansy. And so this is pansy over here on our sled. She has a mass of 60 kilograms. It's on a 15 kilogram sled. So that gives us a total mass. We have to add these two together because Gus is going to be pushing both her and the sled. So we have to have a total mass of 75 kilograms. And the force that's going to be applied is going to be 300 newtons. And so since we're looking for the acceleration, you'll notice I've gone back to the guess method. There's my givens, there's my unknown. And so I'm going to use acceleration is equal to the force divided by the mass. So a force of 300 newtons divided by a mass of 75 kilograms will give us an acceleration of 4 newtons per kilogram, or more commonly known as 4 meters per second squared. Now, Pansy now sits in the same sled, but this time Gus pushes her with a force of 300 newtons across the grass with a 100 newtons force of friction. So for this one, I'm actually going to draw a picture. So, and actually, free body diagram. I know that we have this force due to gravity pulling down, this normal force going back up. The force of Gus, which I'll call F Gus, is going to be that 300 newtons. But now we also have, and I'll change colors here, a force of friction going back. That force of friction is going to be 100 newtons. So we have to use the net force here. And actually, I should probably go back and redefine this from the get-go. This acceleration is equal to the net force applied divided by the mass. And so if there's more than one force acting on this thing, we have to take the vector sum of all forces. So in this case, we have 300 newtons pushing forward, 100 newtons pushing back. That means our net force is going to be 200 newtons because they are equiparallel, and thus we subtract. And so when you take the 200 and subtract that, or sorry, not subtract it, divide that by the mass of 75 kilograms. I was just thinking I probably should have written out the equation, but I did up there, so I'm covering myself good. So 200 divided by the 75, that's going to give us 2.67 meters per second squared. Now, number 4. According to Newton's second law, if two objects are pushed with the same mass and pushed with two different forces, which will accelerate more, one pushed with greater force or pushed with less? And quick reminder, acceleration is directly proportional to the force applied to that net force. And so a larger force will give you a larger acceleration. So the one with a greater force will have a greater acceleration. Now we have Herbert, who has a mass of 50 kilograms. Herman and Herbert are ice skating. Herman pushes Herbert across the ice with no friction. Herbert accelerates at a rate of 5 meters per second per second. Remember, that's another way of putting meters per second squared. How much force is Herman exerting? So for this one, again, going back to our guess, we'd have a mass of 50 kilograms of Herbert. We have an acceleration of Herbert of being 5 meters per second, or meters per second squared, and we're looking for the force. So now I can still use the same equation, A is equal to F over M, but you'll often see me rewrite this to make it F equals ma. All I did was just cross multiply there. So we take the mass, multiply the acceleration, and so my mass of 50 kilograms times my acceleration of 5 meters per second squared will give me 250 newtons. Now we've got Bubba the alien being pushed through space by a rocket pack. Bubba's mass is 75 kilograms, begins with a velocity of 5 meters per second, and in 10 seconds has a velocity of 15 meters per second. What's Bubba's acceleration? So for this one, it's actually an old school one. We have his initial velocity. Initial velocity is 5 meters per second. We have a time elapsed is 10 seconds, and then we have his final velocity as well, is 15 meters per second. And we're looking for the acceleration. So I'm going to go back old school and say, oh, acceleration is the change in the velocity over the time. So that's VF minus VI over T. So 15 meters per second minus the 5 meters per second. Divide that by my 10 seconds, and I'm going to get a 1 meter per second squared as my acceleration. For part B, what force is the rocket pack exerting on Bubba? So for this, I know I have an acceleration now of 1 meter per second squared. And I have a mass of Bubba the alien is 75 kilograms. And so the force exerted, F equals ma, that's at 75 kilograms times the 1 meter per second squared to give you 75 newtons. Scrolling up, a bowling ball is rolled with a force of 15 newtons, accelerates a rate of 3 meters per second. What's the mass of the bowling ball? So again, here I know my force is now 15 newtons. I know that my acceleration is at 3 meters per second, or meters per second squared, and I'm looking for the mass. Question mark. So I'm going to go with the F equals ma again, or A is equal to F over m. If I rewrite this, m becomes F over A. Now, you don't ever have to do this. You don't have to rewrite it like this. I encourage it because, again, once you get into AP, now you start dealing with not just numbers, but also symbols a lot more often. Sorry, I'm in the process of trying to plug in my computer so it doesn't die on me. And I'm feeling, there we go, now it's going. So you don't have to rewrite this like this, but you can if you wish. So if I take the force, which is 15 newtons, and divide it by my acceleration of 3 meters per second squared, that will give me a mass of 5 kilograms. Now it says different bowling balls roll with the same force but accelerates at a rate of 4 meters per second. What's the mass of this particular ball? So in this case, again, same force, so I need to keep my force as being the 15 newtons. But now my acceleration is the 4 meters per second squared, looking for my mass. So mass is equal to force divided by acceleration. So my 15 newtons divided by my 4 meters per second squared, and 15 divided by 4 gives me 3.75, I believe, just double checking. Yeah, 3.75 meters per second squared. Now, kilograms, my fault. Because I'm doing newtons over meters per second squared. Here's the other thing, too. If you don't remember the unit of mass is kilograms, you could just leave that as newtons divided by meters per second squared, and it's still going to be perfectly right. Number 9, according to Newton's second law, if two objects are pushed with the same force, which will accelerate more, object with more mass or an object with less mass, remember that acceleration is inversely proportional to mass. So the smaller the mass, the greater the acceleration. So obviously the choice has got to be less mass here. And number 10, you're purchasing a stereo from a rather untrustworthy store. You suspect the salesman has taken the stereo out of the box, filled with styrofoam instead. Salesman slides the box across the counter with a force of 20 newtons. So the force is 20 newtons on it. The box accelerates at 2 meters per second squared, or 2 meters per second. You know the mass of the stereo is 15 kilograms, is the stereo in the box. So the mass we're looking for here is 15 kilograms. Okay? And so if we take a look at this, that was the force applied onto our mass, giving an acceleration of 2. I can solve for the mass, F over A, so in this case 20 newtons, divided by the 2 meters per second squared. That's only giving me a mass of 10 kilograms. So since I know that the stereo has a mass of 15 kilograms, it's obvious that that package does not contain the stereo. Okay? Now, why you're able to know how much he's pushing it with and able to measure the acceleration and the mass of such stereos and stuff, but not being able to look inside a box, I don't know. It's kind of weird too. But hope that helps, and I hope you learned a little something along the way. So take care. Have a great day. Bye.